titrations begin. Chapter 7. Okay, you probably should mostly be used to titrations at this point. You've done a few of them in Gen Chem, but you may have forgotten all about them by this point. Like a bad dream. All right, so in a titration, a standardized reagent is going to be added to an unknown quantity of analyte until the analyte is judged to be exactly consumed by the reaction. And so you have a reagent, you'll add it to an analyte, it'll stoichiometrically consume. That stoichiometrically does not mean it's 1 by 1. It means that it's either 1 to 1, 1 to 2, 1 to 3, 2 to 3, you know, that a integer number would consume an integer number, okay? So this is a common misconception, by the way, where people think this means 1 to 1. It doesn't, okay? All right, so this is going to give you some sort of product. You will be able to detect the difference in some way. Oftentimes, you'll have an indicator or a spectroscopic method to detect the difference. And then you will stop adding the reagent. You'll be able to measure the reagent and thus, through stoichiometry, measure the analyte. That making sense? So like in the case of acid and base, right? You remember doing this, right? You had like vinegar, you titrated with NaOH, you knew the molarity of the NaOH. And so when you added it, it turned pink because you had phenolphthalein in there. You stopped adding it, you measured the amount of NaOH, you used the molarity to figure out the moles of NaOH, and that gave you the moles of your acid, right? Okay, now there's a common misconception. Everybody thinks that because I'll teach you methods at the end, that you can do this using electric probes, you can do this through spectroscopic methods. A lot of people seem to think that titrations are no longer used, but that's not true. They are. They're incredibly reliable, and they're incredibly well understood because they've been in the system for quite a while, right? Now, there are new methods to do titrations better, but the basic method is the same. It's just like an automatic titrator where you have a thing that can drip very, very small drops for you, okay? So this is the Phoenix Mars 2008 lander. This studied the ionic composition of Martian soil by scooping it up by robotic arms. Unlike other ions, sulfate was actually measured by precipitation titration with Ba2+. And so that's how they get the sulfur amounts in that lander. Okay? I imagine that's probably about used up by now, but yeah. The Ba2+ was added until all of the SO4 was precipitated. The amount of sulfate was determined by measuring the amount of Ba2+ that had reacted. And so they were using this stoichiometric reaction right here, right? Which in this case was 1 to 1. So, but I want to make sure that you know that it does not have to be 1 to 1, okay? Something that people get stuck on all the time. Okay. So here's a titration. You see in the log of the concentration of the molarity. And what we see here is we add a leaching solution right here, and then we get a chloride calibration solution that's added, and that spikes that chloride up. The soil is then added, and the BaCl2 begins to enter the cell right here. This is before that BaCl2 is added. We have a chloride concentration of 0.00019 molarity. We add that, and we get an increase. See that? Notice that these increases are not nicely linear. They always have a rapid up, slow, and then rapid. Okay? And so Right here, you see your chloride concentration is going up. This right here is then the endpoint. After that, you just get straight upwards because it just increases as you add. So this right here would be our endpoint. That's where we detect how much barium we have. And again, the endpoint is when you end. That's when you should be stoichiometrically equal. Okay? Now, your endpoint isn't actually always perfect. Okay, and we'll talk about that a bit more. But first we need to understand titrations, get your reviewed. So what is volumetric analysis and a titration? The increments of the reagent solution, which are called the titrant, are added to the analyte until the reaction is complete. So the analyte, like every other part of this class, is the thing you're trying to determine, right? You're analyzing the analyte. The titrant is the thing you add to it in the titration. Okay? You got the terminology down? Okay. From the quantity of your titrant that you add, that required to complete this, you can calculate the quantity of the analyte that must have been present. And you do it, if you're doing a volumetric analysis, through your simple concentration calculations that we practiced before. So the millimoles of the titrant would be the volume in milliliters times the concentration in millimoles per milliliter. By the way, millimoles per milliliter, you'll notice the millis in front of both. So they could cancel, and you'd be left with moles per liter. So that was molarity, wasn't it? Okay? And that's just an easier way to deal with when you're using milliliters and you have molarities, right? Then you can just do everything in millimole. And that's a titration there. You guys probably remember this. Typically, you do 2 of these and through Gen Chem. 2 titrations. Okay. And we'll do one later on in the semester. All right, so the equivalence point, this is going to occur when the quantity of the added titrant is the exact amount necessary for a stoichiometric reaction with the analyte. The equivalence point is what you're actually trying to find, okay? You're never going to get it perfectly, but you'll try to get as close as you can. So that is the stoichiometrically equal. That's what's equal. So essentially, moles are equal, stoichiometrically at least. What we actually end up measuring is always the endpoint, because the endpoint is when we end, right? And this is going to be marked by a sudden change in the physical property of the solution. This could be color, this could be electrical conductivity, this could be a variety of different physical properties, okay? But it's always going to be, we're measuring it by some sudden change of physical property. Is that making sense? So the difference between the endpoint and the equivalence point, this is actually a titration error. And if you set up a titration extremely well, this error will be very small, and you'll be able to correct for it. Most often, this error is a systematic error. However, if you do a good enough job, it can turn into a random error that you just can't get a small enough drop. So you get on both sides of it randomly. Okay? So the types of titrations, there is a direct titration, and this is the one you're most familiar with. That is, the titrant is added to the analyte until the reaction is completed. This is your typical acid-base titration, where you would take vinegar, you add a standard NaOH to it, and you get the titration, right? That's a direct titration. The other method is a back titration. So you add a known excess of reagent to an analyte, and then you titrate the excess with a second reagent. So essentially, you add something to completely neutralize it, and then beyond. So let's say you're doing did you guys titrate an antacid? in Gen Chem? Okay, this is the most common one that people would experience, is if you want to titrate an antacid, you'd add a standard addition, like 25 milliliters of 0.1 molar HCl, and that's going to completely neutralize and more. So you'll have excess HCl, your antacid tablet, okay? And you do that because the antacid tablet would take too long to react. If you added acid, your antacid tablet would not react immediately. It would lag behind all the time, and you'd never be sure if the reaction is complete. So what you do is you add the acid, digest the antacid tablet, and then you would titrate the excess HCl until it becomes neutral. And you can think of it as how much does something cost? Well, let's say I'm at the counter, I'm buying a piece of candy, and so I hand $1 and the piece of candy to the clerk, and they hand me back 50 cents. How much did the candy cost? 50 cents, yeah. See, I can use the two standards I have to deduce what my analyte is. That makes sense? Yeah, it's actually a lot easier than people think, but they get confused, right? Okay, so standardization. This is the process of determining the concentration of a titrant. The titrant is reacted with a primary standard. Typically, you're not going to use primary standards because the best primary standards are solids that are non-hygroscopic, okay? Which obviously you would not want to try to use to do a titration, right? You imagine that, sprinkle it in, wait 10 minutes, sprinkle it in, wait 10 minutes. It'd be terrible. The validity of the analytical result is going to ultimately depend on knowing the composition of your primary standard. So your primary standard is that place you're making the assumptions. You're assuming that it's pure. You're assuming that you're weighing it correctly. You're assuming that it's going to all dissolve when you do your titration. You have to make assumptions on it, okay? And this is actually one of the places where people screw up the most. They get impure primary standards. The primary standard, these are what a primary standard should be, and these are the assumptions you make when you use a primary standard. You can get primary standards that fulfill these assumptions, but you have to be careful because when you let them sit in environments that they shouldn't be sitting in for long periods of time, they can deviate from these assumptions. The primary standard should be pure enough to be weighed and used directly. So you should be able to weigh it out, and that is the amount you get. A primary standard should be 99.9% pure or better. This purity right here actually limits all the rest of your calculations. For example, a 99.9% purity means you only can use 3 decimal places. There's only 3 sig figs in that. Okay? Anything, if you do a titration and you start saying, I got 4 sig figs, and it was only 99.9% pure, you're not right, are you? Yeah. You're overestimating it. That should not decompose under ordinary storage. Everything decomposes over time, right? So you gotta be careful about this because oftentimes you buy large quantities of this, it's fairly cheap, and you'll think you'll go through a lot, and then you'll find out that it's like 50 years old at the facility, and they're like, we have 70% of it left. You can't throw it away. But after 50 years, it's decomposed. I don't care how stable you think it is, right? We got a problem. What's the time, by the way? Oh, okay. Let's quit here. We'll keep on this.